Thank you, everybody, for having me and getting up bright and early this morning. Okay, so I'm going to talk a little bit about HPC and cloud and the different approaches that we've seen to that out in the wild up to today. And I guess the first bit of housekeeping I want to get out of the way is about what we mean when we talk about cloud. So what I'm talking about here is private cloud infrastructure as a service for research, computing, and HPC. So the other small item of housekeeping here is to tell you where I'm from, and that is the Monash E-Research Centre, and that's a bit of a pictogram of what we get up to. We have a kind of a talisman that we reach for when giving these sorts of slides, which is to talk about the 21st century microscope, which is something that our director Paul Bonington coined. So Monash is a fairly large university by any stretch, 60,000 students, about 7,000 research staff, and an equal number of professional staff as well, across campuses around the globe. And one of the things that we do in the Research Centre is run one of the nodes of the Nectar Research Cloud. Now, probably most of the people here are either from Nectar nodes or perhaps bid on or proposed systems for Nectar sites or their associated storage, so you probably won't be strangers to what I'm talking about here. But Nectar really led the way for research cloud on OpenStack globally, and it's been a real privilege to be part of that project really since it began, back when we were talking about what we should build for the sector in 2011. So that's now sadly 7 nodes around Australia. I'll get to that in a moment. But so University of Melbourne is the lead agent, and one of the things I'm going to cover here today is the system M3 that we built as an extension to Nectar at Monash, which is sort of a private part of the research cloud for particular projects at Monash. So that was the original picture of Nectar. And one thing to note is that this approach of having a single sort of pane of glass for users here with a single set of APIs and dashboard access and this sort of stuff is still relatively uncommon, and there was really no other choice for federation back when the Nectar Research Cloud was first built. And I guess the nice thing about this is that for users, they have a relatively consistent experience and they don't have to deal with multiple regions, which if you've actually done any work programming against cloud APIs, then that's actually not that easy with many of the libraries out there. You end up having to treat, even though you might have a federated research cloud, you end up having to treat each zone like a whole separate system. And it also means that for us running these infrastructure cells, we have a smaller management and control plane footprint, which is quite nice as well. So unfortunately, just recently, Pawsey has pulled out of the research cloud. But of course, they haven't pulled out of cloud computing altogether, and in fact, they're just building their own private OpenStack cloud. And whilst that's happening, it's interesting to see maybe we're having a bit of a shift to the east here, because coming online now is an Auckland node as well. And what's not depicted here is RMIT, which is partnered with Monash, and Swinburne University's partnered with Melbourne as well. So they've both got their own sort of private capacity within the research cloud as well. So it's sort of interesting to see that there's, I guess, a new federation model starting to evolve there, and there's quite a bit of work happening globally to look at models for research, well, particularly research cloud, but just general cloud federation as well, particularly in the OpenStack space, just so that we can, I guess, better empower researchers to get at the resources that they need to do their job. So I want to say a quick thank you to one Swig. That's Stig Telfer from Stack HPC. He is my co-chair on the OpenStack Scientific Working Group, and he also generously lent me a couple of slides that I've stolen from him today. And the other thing that I thank him for is that the Scientific Working Group was really his idea, and he kicked it off and got it going. And I'll talk a bit about some of the other people that are involved there and some of the outputs from it right now, in fact. So Stig works very closely with Cambridge in the UK. And so one of the first things that they did and that he was working on when we met was to build a life sciences focused high performance computing platform for Cambridge, and in particular they wanted OpenStack to provide them with the multi-tenancy and particularly secure multi-tenancy for the kind of work data sets that they were handling in this environment. So they're doing, genome analysis and patient data and this sort of stuff here. So that was kind of the first one, and this is an interesting system because whilst it's more of a traditional OpenStack cloud and that it's using libvirt and KVM, it's very heavy on storage technology, as you can see. So it's got this Nectar stuff in here, plus Ceph and Lustre, and using several different networking backends as well, including SRIOV. Then next we've got Bridges at Pittsburgh Supercomputing Center. So that's a little diagram of Bridges' network topology. It's an omnipath fabric, and I think the size of the nodes are kind of depicted up there. The interesting thing to note about Bridges is that it is managed with OpenStack using Ironic for bare metal provisioning. And they also do some interesting stuff with tying that together with Slurm, their workload manager as well. I was hoping to have a bit more detail to put around that, but about the Slurm integration, but I haven't received any particular info there yet. Although one thing that's happening upstream in the OpenStack world at the moment is that Nova, which is sort of the resource manager part, the compute resource manager part of OpenStack, is refactoring to have a more generic support for having underlying resource providers and management. So there'll be a time, probably within one or two releases, where you can start looking at doing things like having Slurm maybe as your underlying resource manager to look after, say, things might be reservations or what have you, and that plugging into Nova and giving it the information about what resources are available across the system, and then having Nova provide external APIs for people to actually access that as well. Then we've got Jetstream, which is a system. It's a US research cloud run with sites at Indiana, TAC, and University of Arizona, I think. And that's a system focusing on really gateway HPC, and I mean that both in terms of a training ground and also a place to actually run scientific gateways, which they're very heavy on and have a big program in. Chameleon Cloud. Chameleon's an interesting system, notably because it's kind of focused on computer science research, and they actually use an OpenStack project called Blazor to manage reservations on the system, so that when people want time on particular parts of the system or a particular size, they actually have an automated system for doing that as well. So they've got a bunch of heterogeneous hardware and all sorts of stuff. It's kind of a system focused on cloud systems research. And so all those people or their groups are involved in the OpenStack Scientific Working Group. And if you're interested in this space and what people are doing with the intersection of OpenStack, cloud computing, and HPC, it's a really good community to come to. One of the first things we did last year was to compile a list of a set of use cases and publish a little book, which you can get from the that science link there on the OpenStack site. So I guess I'm going to move on now to really Monash's contribution to all this and what we're doing for particular science agendas at Monash, and the learnings in this space that we've been contributing back as well. And talk about Massive, which is, so that's the multimodal Australian Sciences Imaging and Visualisation environment. So it's a specialised HPC facility for imaging and visualisation. So Massive has roughly $2 million in partner funding a year. Various partners, Monash, Australian Sync and Saro, and of course affiliate centres and so on as well. These numbers are probably a good year or so old now, so they're a bit out, but I think we might have just hit around 200 projects. And at the moment, there's a fair amount of effort going on in actually just moving people from the legacy systems to the newer platform as well. So a lot of interactive visualization usage there, as you can see. One of the other related projects run sort of through the Massive umbrella is the characterization virtual laboratory, and that has a lot of national partners as well. But Bethwaite, who runs the Massive project, runs the CVL project as well. And one of the other key things that Massive is focused on is instrument integration. So you may be aware that we happen to have a synchrotron just across the road from Monash Clayton. So that has a number of instruments sitting around it as well, notably the imaging and medical beamline, IMBL. We have a cryo-EM at Monash as well. We have the Monash Bioinformatics, what's it called? MBI is the, I've forgotten the acronym. Never mind. Thank you. The one interesting thing about Massive, and that I guess colours the kind of workloads and so on that we see there, is that there's a large cohort of researchers that are actually new to HPC as well, and that's why the interactive environment is a very important part of that project as well. It's also key when you think about the kind of workflows that people using this system are performing as well, and I'll get to an example of that with the cryo-EM in a moment too. So imaging HPC is, I think we see that as a big domain going forward. Particularly at Monash, we have sort of new large data generating instruments coming online at a fairly steady rate. Major ones perhaps every 6 months, and then other smaller ones, just interspersed amongst there as well. Often we don't find out about them until about a few months before they are about to start producing data for the first time, and that can cause a bit of a scramble. Fortunately, with the cryo-EM, that didn't happen in that manner. So new instruments and techniques are really driving this need for high performance computing in imaging. And so we've got things like the cryo-EM, lattice light sheet, and other nuclear imaging, and so on. There's also one of the interesting things about some of these workflows is that you want to design a workflow that can give you real-time feedback in the experiment as well. Some of these new microscopes are capable of live cellular imaging, so being able to actually change the specimen during the experiment is a very powerful thing. You know, you've got somebody who's worth a lot of money themselves with a specimen that may not last more than a few hours, wanting to do some imaging on a system that needs to be booked and is worth quite a lot of money. You want to make sure that they're getting good data while they're there at the instrument. And so that means having the compute pretty well coupled with the imaging so that you can actually see what you're getting. Another interesting thing here is to see the influence of new deep learning and AI techniques as well. We've already started to dabble a little bit with this. We're fortunate to have a partnership with NVIDIA, which has meant that we've had a DGX1 sitting around to play with that wasn't even ours. They just sort of leave it on campus so that when they need to take it to a customer, they can come and pick it up. And in the meantime, we get to play with it. And some of these techniques can be applied very well to this sort of science. I mean, particularly there's obvious use cases in actual, hospital imaging and what's the term? Diagnosis. Sorry. But this is one thing that's pretty obvious if you start looking at some of this data is that it's really hard to see detail here as well. And that's where some deep learning techniques are actually starting to shine too. So a quick example of what we get from one of these instruments. So this is the Titan Krios cryo-electron microscope. So this thing fires an electron beam at a sample that is cooled to near absolute zero, and takes a whole bunch of pictures of it from various angles. And then you get data that looks a bit like that. So there's a number of problems with the data to start off with. Firstly, the electron beam itself causes a heck of a lot of movement of the image in the sample, which has to be kind of deconvoluted. If you zoom in, you can actually start seeing perhaps a little bit of structure there. So you've got an experimental slide that's got a bunch of the interesting molecules on it here, or interesting structures, and you can see they're all at different orientations and all sorts of things. We don't know what orientation they're going to be in. So there's a whole bunch of image processing steps here to try and pick those things out, make sure they don't have any occlusion from other neighbouring structures, figure out what orientation they're at, and then eventually, once you go through a bunch of steps, you get up to sort of 2D refinement, and then you can start seeing structure, and then you go into 3D refinement, and you start getting these sorts of pictures. And that workflow has about, I think it's about 9 or 10 processing steps that are all quite distinct and take various amounts of time and use tools that can or cannot benefit from GPU acceleration today. So these sorts of workflows are quite interesting to design a system for. And this is really one of the primary workflows that we built M3, the next system in the massive series of computers to work on. And this is a quick picture of the workflow. So there's a microscope. Obviously, we're capturing data. There's a local PC, of course. There always is. It's probably running Windows 98. Yeah, somebody feels that pain. So we, at the point of capture, we try and start the data management process here. So we move on to, we use a tool called Mitatis, which a number of people are aware of, and that's copied to our research data storage, and then also to the HPC system. So at this point, the scientist then has access to, they've got a few workstations sitting around the lab that they can have a quick look at some of this data on, but it's also been copied to massive. So if somebody has come to the facility can walk away with their data already on HPC and then go back home or jump on a plane and then get onto a scientific desktop environment which gives them the visualization tools and indeed all the tools that they need to use to do this workflow with a stack of images here. And to give you an idea, we're talking about data sets that are of terabytes or more, especially as they keep adding higher and higher resolution cameras to these things as well. So the Almond laboratory at Monash, one of the tools that they develop is this thing called Simple, which is quite an important code for us. I'll talk a little bit about that later too. So that does the structural refinement part, 3D reconstruction. So at the moment we have 120 cores dedicated just to running that part of the workflow, so that we can make decisions as you capture. So moving on to M3 and the OpenStack stuff that underneath that. So when it came to M1 and M2 are the original systems in Massive, and there's a couple of people around the room that worked on the build of those. They're getting pretty long in the teeth now. M1 is to be, I think, decommissioned at the end of this year. Finally, that's at the Australian synchrotron. M2's hobbling on a little longer yet. We're about to add a stage 2.1 to M3 to accommodate the final, the final migration of users off M2. So this system started off with a mixed GPU and CPU capability. The image processing that we do in the Massive project, of course, lends itself pretty well to a lot of GPU gear. We added a bunch of P100s earlier in the year as well, so we've got a rack of those now too. And we're about to expand Luster and add a little bit more compute too. So when it came to deciding how to run this thing, we decided to do it with OpenStack. But also to do so in a manner that meant that we could hedge our bets slightly too. Of course, it's not everything in here is running OpenStack. I mean, the Luster node, the OSSs, for example, are not part of OpenStack at present. So that's really just about designing the network to integrate with non-OpenStack managed gear as well. And so the main thing there is really is not relying on any of the tunneled style networking, which is routed within the OpenStack cloud. So we use all external routing and so on for this system, and indeed all of our systems. Although if you're interested in VXLAN and pushing the boundaries of network performance, virtualized network performance, then Stig Telfer, who I mentioned earlier, did a talk at Lugano, where he sort of delved into some of that in quite a lot of detail, and some of the findings that they've made there with some of the work he did at Cambridge was very interesting. So why OpenStack? So of course we've got heterogeneous user requirements. We can't really build a system anymore with the expectation that it's going to do the same thing for the next 5 years. And so that the flexibility at the infrastructure level is very important. And of course, clusters need provisioning systems anyway. So, why not use one that gives you a bit extra, that lends itself to multi-tenancy and actually letting people have at it. At the end of the day, this is actually what the users want too. Plus, we have, we not only run HPC services on top of this infrastructure, as in what the users think as the M3 system. They log into a head node just like any other regular HPC service and use the queuing system and so forth. But we also have a bunch of users that don't want anything to do with a queuing system. In particular, bioinformaticians still don't like that most of the time. And at least with an environment like this, we then have the flexibility to give them what they want, but with the capability to have tight integration to the HPC as well, and also with access to the high-performance file system and all that sort of stuff that they don't normally get if they're just sitting off in a separate private cloud environment with only access to volume storage or something like this. But one thing that you hear quite a bit is, OpenStack is complicated. It's interesting to reflect on. I actually put this slide together, I think maybe a year ago, and then looked at it again the other day and realized this is, I think at least from my narrow view, that this has changed quite a bit. The foundation, the OpenStack Foundation, that is, has done quite a lot of work, I think, to sort of simplify the project landscape within OpenStack for people that are new to OpenStack, so that when they sort of come along and ask what is this thing, they are not so totally bombarded with 30 or 40 different projects, of which they only need 4 or 5 to run their cloud. And yes, of course, OpenStack actually is complicated because it's essentially doing data center management for you. So one of the things that we needed to tackle for M3 for the virtualized parts of the computing environment was tuning. And I've got a few slides on this and some of the numbers that we collected, and also some comments about, I guess, the things to watch out for. It's not all beer and skittles as well. You have to be prepared if you're going to start doing HPC work in a virtualized context, like we are here. Then you also have to be prepared for some pain as well, and to spend a fair amount of time figuring out where your bottlenecks are. Often those bottlenecks are there all along, but you are amplifying them by putting them into a virtual environment, so you start seeing them more. So key tuning for HPC on OpenStack, and really this is not particular to OpenStack. This is really about KVM. It could be applied to Zen as well. VMware have a similar story. The nice thing is that OpenStack exposes all these features quite simply to the end user, and you have a few different choices about how you want to expose that as a cloud architect. You can create virtual machine flavors that users have access to when they're booting a machine, that have things like the NUMA topology and all that sort of stuff built into them. Or you can let them add that metadata themselves. Say they want to play around with it, figure out what's best for their workload, then they can actually specify that stuff too by decorating the image that they want to boot with particular properties, and then booting that. So anyway, the key things here are obviously passing through all the CPU instruction sets that you've just paid for. If you just run a naive version of KVM QEMU, then you'll be getting a CPU model that limits all the feature flags so that you can do live migration. In this context, if you're doing HPC work, then you may well not care about that. Or if you do, then you'll be happy to only live migrate between host machines that are the same, rather than having multiple different models of CPU supported. There's certain kernel consolidation features that you would normally have on for a cloud environment, like same page merging, that will hurt you in a HPC context. Of course, there's a lot of potential network overheads depending on how you choose to do your networking, and Stig talked a lot about that in his talk. What we did for M3 was basically circumvent that straight away by using SRIOV for the main data networks that we integrate into the system. So for the Lustre file system and for any parallel job traffic as well. And huge pages, of course, are an important factor as well. TLB thrashing sucks. So that's that gives you a quick Mellanox propaganda slide of the difference between your network latency with going through a virtual networking stack as opposed to passing the device through to the guest. Nice thing about SRIOV is that that's a PCI standard that is actually designed for this, as opposed to GPU pass-through, which I'll get to in a moment. So our high-performance file system integration looks a little bit like this. You've got the virtual functions being passed through to the guest, and bare metal Lustre servers down the bottom here, guests on compute nodes, etc. Not much more to say about that, except that this means that for this particular fabric, we're using 100 gig Ethernet, and doing this SRIOV pass-through then also means that we can run RoCE traffic, so RDMA over Ethernet, and use Lustre O2IB driver for Lustre ALNet. And this is another little graph I've shamelessly stolen from Stig, but this is one sort of thing that illustrates some of the fabric design requirements that we looked at when building the system. We saw a similar picture to what Stig and co at Cambridge saw when we looked at past job stats, which is that you have a huge number of single or two-core type jobs and a whole bunch that use the whole node, and then not a heck of a lot in between. I mean, this slide doesn't show you CPU time, of course, so it's just favoured against, it's just looking at job counts. But this was borne out in the data that we had from other systems at Monash as well. And so that meant that when it came to designing the network fabric for this system, we decided it was probably not a great investment to drop, up to like 40% of the system cost on network fabric. Sorry, Sudha. And just design the fabric mainly for the file system requirements. And if you think about that, that's not even a major limitation for us, because today that means that for, say, 28-core server connected to a 100 gig switch, you can still run a 1500-core job with full 50 gig non-blocking bandwidth, which is still a fairly large job in anybody's book for this sort of computing, right? And anything else can go to NCI or PORC, right? It's a fairly, that's a fairly large training ground. Thanks. So we, instead of going, I guess, with a typical HPC interconnect, we went with Ethernet, as I said. We now manage that with Cumulus Linux across the switches, which is good fun. The nice thing about this is that this is a pretty scalable architecture, right? We've got layer 3 routing in the fabric when we need more bandwidth going up. Of course, we've left a few ports available on these leafs so that we can upgrade that if we need to. We can add more spines in and keep going out to the side. And as I said, having Ethernet here means we don't have any special fancy bridge boxes going on anywhere to link out to external routing. And for a cloud environment, that's quite important, because not only are we running HPC stuff on this fabric, but there's also people that are doing really north-south focused work, right? Or integrating with stuff on the campus, running services, this sort of thing. I'm just going to jump on quickly because we're getting low on time. So a quick snapshot of the compute performance. We did a bunch of benchmarking, of course, when we got this system, and for the tuning work that we did on KVM. These numbers that I'm about to show you are from a Haswell box with 256 gig of RAM. The guest is 240 gig of RAM. It's got GPUs, all that stuff. So this is what happens so the blue line up here is optimized One is obviously the ideal, so this is relative to bare metal. And you've got the naive yellow line, which is actually what happens when you don't do any of the tuning I mentioned, like without pinning or without the NUMA pass-through. This is high-performance LinPack. Turns out LinPack is actually a really terrible thing to use for this because it runs quite well anyway. I mean, as you can see, we haven't done any tuning here yet. Once we get up to large problem sizes, we're already about 94% of bare metal. The green line is what happens when you accidentally flip the NUMA mapping. So you're binding everything to the wrong cores on the other side of the QPI bus. Likewise, then we also checked with the Intel LinPack, the SMP version, and that scale, I mean, that sort of scales even better, even at small problem sizes. So, all great, right? Well, not quite. What we didn't do initially was have huge pages turned on for that test, because turns out that the huge page allocation in the kernel is single-threaded, and when you start a guest that is 240 gig of RAM in size, it takes longer than 30 seconds to zero those pages, and then libvirt times out and QEMU gets killed. So you can't start your machine. The way around that is to use transparent huge pages instead. And turns out that actually that works equally as well as using static huge pages on the host. If your host is starting from the point of boot, you don't have major memory fragmentation in the first place, then you'll get complete backing of huge pages with transparent huge pages. So that unicorn poop was this outlier down here. Once we started letting people onto the system in the initial testing phase, we started seeing a few weird results coming out. Outliers here and there that didn't follow any particular pattern on the nodes or anything like that. There was no obvious thing going on there. And once we zoomed into this a bit more and collected some more numbers, then we realised that this was because we had put off huge pages essentially. And this is, now you see what happens once you get them. We've now got much more consistent performance again. And if anybody's going, why is the huge page back to VM better than the hypervisor, then the best explanation I have for that is because they're different kernels. But it's interesting, you do actually see patterns like this emerging quite a lot, and a lot of people just sort of go, meh. But there's so many, there's so many knobs in the Linux virtual memory manager that the difference between kernels or a few syscontrols is a major thing, and I would put that down to most of what you see in those sorts of graphs. But it's also important to recognise that this is not the complete story here for tuning. You will also find codes that hit the TLB very hard, and if they can't get huge pages backing both of the guest and inside the guest for their own virtual memory, then they'll suffer a lot. You see that both when they're run on the bare metal and in the guest, but it's amplified inside the guest. And it's interesting to note that in certain scenarios, for example, when the page cache is full on the system, that memory allocations, you might be surprised to know, but when a memory allocation happens, you do a malloc, kernel just says, sure, fine, have it. But the memory hasn't actually been put aside for the process. Once the process actually tries to touch it and page faults, then you go into this dark web inside the kernel where you might end up, if you have transparent huge pages turned on, you might end up then compacting memory so that you can allocate huge pages. So for some codes, you'll see them spending a huge amount of system time with a K huge page D thread running because they're spending most of their time dirtying memory and the kernel's trying to keep up and compact. Or you'll see codes that have failed to allocate huge pages because of the memory state on the system, and then run slower because they're thrashing the TLB. So you have to, if you're running an environment like this and you're sensitive to your performance, which of course it's HPC, so you have to be watching out for this stuff. And there's a few tricks that you can do to try to lessen the extent of it as well, like dropping caches in between jobs and things like this. Surprisingly helps. And we're doing a bit of work at the moment looking at newer kernels and the effective zone reclaim and stuff like that as well. But I don't have any stuff on that to share at the moment. So I think I'll leave it there for now, given we need to get on with the time. I've got a bunch of slides about doing GPU pass-through in OpenStack as well, but you can grab these off the interwebs later if you're interested in this. One thing I would say about that is that I was quite interested to hear the talk on RCUDA yesterday, because the more work that I've done in this space with the GPU pass-through, the more apparent it is that there are gremlins there, particularly in the PCIe spec. Google has done a lot of work earlier in the year. They published some blogs on this about fuzzing PCIe devices for security. And it turns out that, of course, when people are designing a PCIe accelerator card or what have you, usually they make an assumption that if some process on the host has access to the device, then it also has root context. And there's other bits and pieces inside that spec which do things like cache virtual memory translations on the device. So if you have a buggy device that can be compromised, then that device can access the entire memory space of the host, for example. So a few things to watch out there if you're actually trying to design a untrusted multi-tenant cloud environment and do this. Okay, I'll leave it there.